Every sound you have ever heard is a lie. Or rather, every sound you have ever heard is a conspiracy between dozens of pure tones pretending to be one thing. A piano note, a siren, your mother's voice, none of them are single sounds. They are crowds. And in 1822, a French mathematician figured out how to arrest every member of the crowd individually. His name was Joseph Fourier, and the tool he built is the single most used mathematical idea in the modern world. It hides inside your phone, your Wi-Fi router, your MRI scan, every JPEG you have ever seen, and every song you have ever streamed. This is what a Fourier transform actually does, why it works, and why it is everywhere. Let's start with the simplest possible sound. A pure tone. A single frequency. Imagine a speaker cone pushing air forward and pulling it back, smoothly, over and over, at exactly the same rate. Plot that motion over time and you get a sine wave. One smooth, rolling curve that repeats forever. A pure tone at 440 Hz is the note musicians call A above middle C. The speaker vibrates 440 times per second, and your eardrum copies that vibration faithfully. Simple. Clean. Boring. Now here is the interesting part. Almost nothing in the real world sounds like a pure tone. When you pluck a guitar string tuned to that same A, you do not hear a clean sine wave. You hear the fundamental at 440 Hz, plus a second vibration at 880, plus a third at 1320, plus a fourth at 1760, and on, each one quieter than the last. Those are the harmonics. And they are what give the guitar its guitarness, as opposed to the piano-ness of a piano playing the exact same note. Same fundamental. Different crowd. So what does the combined wave look like? You add them. Literally. At every instant in time, you take the height of wave 1, the height of wave 2, the height of wave 3, and you add them together. The result is a messy, complicated, jagged waveform that looks nothing like a sine wave. But here is the staggering claim that Fourier made in 1822. Any periodic signal, any signal that repeats, can be decomposed into a sum of pure sine waves. Not approximately. Exactly. No matter how jagged, how spiky, how absurd the shape, there exists a collection of sine waves, each with its own frequency, amplitude, and phase shift, that when added together reproduce it perfectly. A square wave. A sawtooth wave. A shape that looks like a staircase having a bad day. All of them, secretly just sine waves in a trench coat. This is Fourier's theorem. And when people first heard it, they did not believe him. There is a beautiful way to visualize what is happening. Forget waves for a moment. Think about circles. Put a dot on the edge of a spinning circle. Watch its vertical position over time. It traces out a sine wave. Now attach a second, smaller circle to the edge of the first one. Let it spin at a different speed. The dot at the end of the second circle traces a more complicated path. Add a third circle. A fourth. A 10th. Each one spinning at its own frequency, each one a different size. The path the final dot traces becomes increasingly intricate. And here is the astonishing part. With enough circles, you can draw anything. A square. The letter A. A portrait of a cat. The outline of the entire European continent. This is not a metaphor. This is literally what the Fourier series does. Each circle is one frequency component. The radius of the circle is the amplitude. The speed of the circle is the frequency. And the starting angle is the phase. Stack enough spinning circles together, and they will trace out any closed curve you can imagine. So far we have been talking about building a signal from a known recipe of frequencies. The Fourier transform goes the other direction. You hand it a messy, complicated signal, and it hands back the recipe. Every frequency present in the signal. How loud each one is. And how much each one is shifted in time. Think of it as a prism for sound. White light goes in, a rainbow of colors comes out. A complex waveform goes in, a spectrum of frequencies comes out. The formula itself looks intimidating at first glance. An integral from -infinity to +infinity of the signal multiplied by a spinning complex exponential. But the intuition is simple. For each candidate frequency, you wrap the signal around a circle at that frequency and ask, does the result bunch up on one side, or does it cancel out evenly? If it bunches up, that frequency is present in the signal. If it cancels, that frequency is absent. That is the entire idea. Wrap. Check for bunching. Repeat. Your ear already does this. The cochlea, the snail-shaped structure in your inner ear, is essentially a biological Fourier analyzer. It is a fluid-filled tube lined with thousands of tiny hair cells, each one tuned to resonate at a specific frequency. High frequencies vibrate the cells near the entrance. Low frequencies vibrate the cells near the tip. When a sound wave arrives, a chord, a voice, a car horn, the cochlea physically separates it into its component frequencies and sends each one to a different nerve fiber. Your brain receives not the raw waveform, but the decomposition. The spectrum. The recipe. You have been doing Fourier analysis since before you were born. Fourier just wrote down the mathematics. This is why every piece of digital audio you have ever heard relies on the Fourier transform. When you record a sound, a microphone captures the raw waveform and a computer samples it thousands of times per second. A CD uses 44,100 samples per second. That is a lot of numbers. But most of those numbers are redundant. If you transform the signal into the frequency domain, you discover that most of the energy sits in a handful of frequencies. The rest is negligible. MP3 compression works by running a Fourier-like transform on small chunks of audio, identifying which frequencies your ear will not notice are missing, and throwing them away. The file shrinks by a factor of 10. You do not hear the difference. Fourier made that possible. And it is not just audio. The JPEG image sitting in your camera roll right now uses the exact same trick, adapted for 2 dimensions. Instead of frequencies in time, think of frequencies in space. A photograph is a grid of pixels. JPEG divides that grid into 8 by 8 blocks, 64 pixels each. Then it applies a variant of the Fourier transform called the discrete cosine transform to each block. This converts 64 pixel brightness values into 64 frequency coefficients. The low frequency coefficients capture the broad shapes, the overall light and shadow, the general color. The high frequency coefficients capture sharp edges and fine texture. The key insight: your eyes are far more sensitive to gradual changes in brightness than to fine detail. So JPEG aggressively rounds the high frequency coefficients down toward 0, sometimes to 0 outright. The image shrinks dramatically. You barely notice. That is why a 10 megapixel photograph fits into a 2 megabyte file. Fourier, adapted for space instead of time, is doing the heavy lifting behind every photograph you have ever texted. Once you see it, you cannot unsee it. The Fourier transform is everywhere. Noise-cancelling headphones use it to identify and subtract ambient frequencies in real time. Radar systems use it to extract the speed and distance of a target from a reflected radio pulse. X-ray crystallography, the technique that revealed the structure of DNA, is a Fourier transform applied to the diffraction pattern of X-rays bouncing off a crystal. MRI machines build their images by applying inverse Fourier transforms to radio signals emitted by your hydrogen atoms inside a magnetic field. Earthquake seismology, speech recognition, Wi-Fi signal processing, quantum mechanics, the analysis of ocean tides, the design of bridges, the compression of Netflix streams. All Fourier. It is not an exaggeration to say that the Fourier transform is the most widely applied mathematical tool ever invented. And then, in 1965, 2 mathematicians named Cooley and Tukey published an algorithm that made it fast. The fast Fourier transform. The FFT. Computing a Fourier transform the naive way takes n-squared operations. A million data points means a trillion calculations. The FFT does it in n log n. For that same million points, that is about 20 million calculations instead of a trillion. A speed-up of 50,000 times. This single algorithm made digital signal processing practical. Without the FFT, your phone could not decode a Wi-Fi signal fast enough to stream a video. Without the FFT, medical imaging would take hours instead of minutes. Without the FFT, Shazam could not identify a song from a 4-second clip. Gilbert Strang, the MIT mathematician, once called the FFT the most important numerical algorithm of our lifetime. He was not exaggerating. Joseph Fourier himself had a life almost as strange as his mathematics. He was orphaned at 9, educated by monks, nearly guillotined during the French Revolution, and then appointed by Napoleon to govern a chunk of Egypt. In Egypt, he became obsessed with heat. He wanted to understand how heat flows through solid objects, why a metal rod, heated at one end, gradually warms along its length. His answer was the Fourier series. Decompose the temperature distribution into sine waves, and each one decays at a rate determined by its frequency. The high-frequency wiggles die off fast. The low-frequency trends persist. His peers, Lagrange, Laplace, Biot, were skeptical. They did not believe that arbitrary functions could be represented as sums of sines. It took decades for the mathematical community to accept that Fourier was right. He did not live to see the vindication. He died in 1830, at 62, apparently from a combination of heart disease and an obsessive habit of wrapping himself in heavy blankets, convinced that heat was the foundation of all health. The man who solved heat conduction may have died from too much of it. Every sound is a crowd of pure tones. Every image is a mosaic of spatial frequencies. Every signal, no matter how complicated, can be pulled apart into simple, spinning components and reassembled without losing a single detail. Fourier gave us the mathematics to do it. Cooley and Tukey gave us the speed. And the result is a world in which your phone can compress a photograph, your headphones can cancel noise, your doctor can see inside your brain, and a streaming service can deliver a symphony through a wire thinner than a hair. All because a French mathematician, wrapped in blankets and dreaming about heat, asked what a wave is really made of.